We want to determine if a coin is fair. Like all coins, it has a certain tendency to land on heads when tossed. We can represent this tendency with the Greek letter theta, which can take any value between 0 and 1. 0 means the coin never lands on heads, 1 means it always lands on heads, and values in between mean it sometimes lands on heads and sometimes lands on tails, as long as it's tossed enough times. A coin is considered fair if theta is close to 0.5. However, the probability of theta being exactly 0.5 is 0, since 0.5 is one of infinitely many numbers between 0 and 1. So instead, we'll say that a coin is fair if theta is between 0.4 and 0.6. We toss the coin 7 times and observe that it lands on heads 4 times and tails 3 times. Can we conclude that the coin's theta is between 0.4 and 0.6 based on this result? The answer is no. From the 7 tosses, we can only conclude that theta is neither 0 nor 1, since there have been instances of both heads and tails. However, the result doesn't rule out other possible values of theta. In fact, theta could have been less than 0.01, and we're just lucky to see heads 4 out of 7 times. But can we determine the probability that theta is between 0.4 and 0.6? Yes. Mathematicians developed the beta distribution to tackle such questions. Its formula may seem intimidating, but it's based on a simple and elegant idea. In this video, we'll explore this simple and elegant idea using elementary calculus and probability. Let's begin. First, we generalize the question. Given a coin landed on heads h times and tails t times, what's the probability that theta falls between m and n? This is challenging. When stuck, try solving a simpler problem by inverting the original one. If we know theta, can we find the probability of seeing h heads and t tails? This is easier. We observe heads, and so on, h times. We observe tails, and so on, t times. We list all the heads first, followed by all the tails for simplicity. However, as we shall see, the order doesn't matter. The probability of heads is theta, so the probability of tails is 1 minus theta. The probability of seeing heads h times is theta multiplied by theta and so on, or theta to the power of h. Similarly, the probability of seeing tails t times is 1 minus theta multiplied by 1 minus theta and so on, or 1 minus theta to the power of t. The overall probability is theta to the power of h times 1 minus theta to the power of t. In our example, with theta being 0.3, the probability of observing 4 heads and 3 tails is 0.0028. Awesome! We've solved the probability of observing an outcome given a specific theta. The original question is, what is the likelihood of theta being a certain value given a specific outcome? To see how these two values are related, we turn to an everyday example involving a car's make and power system. We come across a hybrid car. Given that it's a hybrid, what's the probability it's a Honda? We can calculate this by dividing the number of Honda hybrid cars by the total number of hybrid cars. The numerator breaks down into the fraction of Honda cars that are hybrids times the total number of Honda cars. Similarly, the denominator breaks down into the fraction of Honda cars that are hybrids times the total number of Honda cars plus the fraction of Ford cars that are hybrids times the total number of Ford cars, and so on, summed over all car companies. We often use this idea without knowing it, but it goes by the name of Bayes' theorem. If we plug in corresponding pieces from the original question, we see theta's likelihood given an outcome equals the probability of outcome given theta times theta's likelihood divided by the probability of outcome. The denominator can be rewritten as the probability of outcome given theta times theta's likelihood, integrated over all possible thetas, similar to how we summed hybrid cars from all companies in the earlier example. Here, theta's likelihood is known as the prior, or the prior belief about its probable values before tossing the coin. Since we're dealing with a previously unknown coin, our prior belief should be that all possible values of theta have an equal chance, aka the principle of maximum entropy. In math, we say p theta follows a continuous uniform distribution with support from 0 to 1. This means p theta is equal to 1 for all thetas, so these terms disappear from the equation. We now have beta distribution's probability density function, aka the PDF. It is that easy. Let's simplify the math to make it more convenient to work with. The numerator is easy to compute, but the denominator can be reduced to a more elegant form. This integral, called the beta function, is tricky due to the exponents. However, since h and t are always whole numbers, if we can lower one exponent to 0, integration will be straightforward. The technique, integration by parts, fits the bill perfectly. Recall its formula. We will assign 1 minus theta to the power of t to u and assign theta to the power of h d theta to dv. After applying integration by parts once, the first term becomes 0 when evaluated from 0 to 1. Factoring out the constant coefficient, we recover an integral identical to the original, except the exponent on 1 minus theta has decreased by 1, and the exponent on theta has increased by 1. Taking advantage of this recursion, we can apply integration by parts again to decrease the exponent on 1 minus theta. We can repeat until the exponent reduces to 0. At this point, the integral simplifies to that of a polynomial, which we can solve and evaluate from 0 to 1 to get 1 over h plus t plus 1. Multiplying the fraction, we re-express the numerator as t factorial. The denominator reminds us of h plus t plus 1 factorial, but it is missing a chunk, so we multiply both the top and bottom by h factorial to complete the factorial in the denominator. We now have a more computationally tractable beta function without an integration sign. Substituting it back to the original formula and rearranging terms, we get the beta distribution PDF in its simplest form. We made it. Next, let's see how the PDF curve changes with different values of h and t. If we observe no heads or tails, the PDF is a continuous uniform distribution. This makes sense because if both h and t are 0, we haven't observed any outcome, so p theta is just the prior. If we observe one head and no tails, the PDF is a straight line with a high at 1 and a low at 0. This is also intuitive because the outcome eliminates the possibility of theta being 0. If we observe one head and one tail, the PDF is an arch with a peak at 0.5. P theta is 0 at 0 and 1, which is again intuitive. After tossing the coin a few more times, the arch grows taller and narrower, indicating increasing confidence in the likely range of theta. We also notice a pattern. The peak, or mode, is always h divided by h plus t. It doesn't take too many more tosses before the curve starts resembling a spike, as our confidence converges towards the mode. But wait a second. The formula we derived appears to differ from the one shown earlier in the video. That formula has these strange symbols and subtracts 1 from the exponents. I am glad you asked. Remember, h and t are always whole numbers in our coin flip problem. But mathematicians often seek generalized solutions for broader contexts, such as cases where h and t can be any non-zero real numbers. Let's assume our derived formula still holds under this relaxed condition. The exponents are fine since we are allowed to have fractional exponents, but factorials are undefined for fractional values. For example, 0.462 factorial is meaningless. Fortunately, there's a way to generalize the factorial function to all real numbers except non-positive integers. That function is called the gamma function, which is where the strange symbol comes from. Gamma of I is equivalent to I minus 1 factorial for all natural numbers I, while the gamma function itself is defined for all positive reals. If we define alpha as h plus 1 and beta as t plus 1, we can substitute them into our derived formula. By the gamma equivalence to the factorial, we get the formula from the video's start. To prove this result rigorously, though, we must start from the gamma function's formal definition and work backwards. I'll include a link to the proof in the video description, but I won't cover the proof here. Among its many benefits, the gamma function unlocks new shapes that can't be described with only whole numbers h and t. For instance, when alpha and beta are both 0.5, the PDF follows a U shape with a trough at 0.5. P theta is undefined at 0 and 1. When alpha is 1.5 and beta is 1, the PDF increases in theta. When alpha is 0.5 and beta is 1, the PDF decreases in theta, where p theta is undefined again at 0, but I digress. Let's return to the original problem about fair coins. We have the probability density function, which gives the likelihood of theta at every possible value. However, the question is ultimately about probability, such as the probability that theta is between 0 and 1, which is the same as asking for the sum of all the likelihood from 0 to 1, or equivalently, the area under the PDF between 0 and 1. We already know the answer must be 1, because total probability must add up to 1. We can also verify that our formula gives 1 by integrating the PDF from 0 to 1. Finally, to answer the question posed at the beginning of the video, we need to evaluate the same integral from 0.4 to 0.6. The result will be the probability that the coin is fair. Normally, textbooks stop here, but being stuck with an integral is hardly satisfying. So in the next video, I'll demonstrate how to apply integration by parts to make the formula computationally tractable. I will also introduce the PDF's close cousin, the cumulative distribution function, aka CDF. So stay tuned.